Yeah, so today I'm going to talk about vector databases in computer vision and how they're kind of changing the field, and a little bit about what I'm going to be talking about. So first, we're going to be going over what a vector database is. A lot of the speakers today, I think, are all coming from a vector database background. As the first one, I'll try to give like an overview of what they are, why we use them, and then kind of move on to some cool things that we're doing with them. The next area that I'm going to talk about is the reverse image search, one of the probably core and main uses of vector databases in computer vision. And then I'm going to move on to reverse video search, which I think is kind of the next step, and a quick demo at the end of both use cases. So a little bit about myself. My name is Philip. I'm a software engineer here at Zilliz for the past 2.5 years. I've been working on a few of our projects. If you've been in our Slack, I've probably talked to you as well, kind of here and there, everywhere. Yeah. So a little bit about Zilliz. We were founded in 2017, and we are headquartered in the Redwood Shores in the center of the Bay Area. We've been kind of focusing on unstructured data since the start. Our main project is the Milvus vector database that we donated to the Linux LF and AI Foundation. We also have TOE, which is kind of our unstructured ETL pipelining software, and that one's also growing. And then in terms of the new LLM wave, we released GPT Cache, which is a caching layer for LLM calls. And yeah, a few of the other projects here, I don't think I need to go over all of them, but those are the ones. So let's get started with what is a vector database. I think this is pretty important. Again, most of the speakers here are from vector databases, and why not kind of give an intro to the general idea about them right at the start. So a vector database is a database that is purpose-built to store, index, and query vector embeddings that were primarily generated from unstructured data. And in this case, unstructured data is any data that does not have a predefined format or a format that's easily comparable by a machine/computer. The most popular ones you can think of are images, audio, text, and a few others. Each domain has their own sort of type. Images are considered unstructured data because even though we kind of know how many pixels there are, what each of the values are, like how RGB image is formatted, when you go to actually compare the images, you don't really know what's going on in the images. If you shift an image by 1 pixel, most of your comparisons are going to break if you're doing pixel to pixel comparisons. And this means that the computer doesn't really have a good way of comparing it. Same thing happens with audio, same thing happens with text. If you change the ordering of text, if you change a synonym of a word in a text, it breaks the computer's understanding of what that data is. So how do we deal with this data? Recently, but not too recently, deep learning models came out, and deep learning models allow us to allow computers to understand this data. They break down the data into vectors, and these vectors are easily comparable. Data that's two pieces of data that are similar to each other passed through the same deep learning model for embedding will generate vectors that are very close to each other in terms of L2 or IP cosine distance. And two data points that are very different will be very far away from each other. So with this, we can then start performing similarity searches to kind of figure out more details about our data and kind of learn about what we have and what we've stored. So what exactly is a purpose-built vector database? I think there's a bunch of different definitions popping around, different projects. So I think this is kind of what I view as what's required to be a database. I believe pretty much everyone has it at this point. The first case is advanced filtering. So you want to be able to filter over scalar data. So it's not just a simple lookup. You want to have actual abilities in the database and to be able to kind of group different results in different areas. You need durability. So you can't just rely on snapshots. I think every time you write data, you should be pretty sure that's going to be saved, even if the system crashes. Replication and high availability, that's pretty self-explanatory. And kind of list goes on. And these are all things that you can find in normal traditional databases. But the reason that normal traditional databases don't work is because dealing with vector data itself is pretty difficult. Traditional databases are pretty inefficient with high dimensional spaces. Sure, they can work in the small sub-million range where doing a brute force search across everything works. Once you start scaling out to billion scale, everything begins to break. Searches take on the order of tens of hundreds of seconds to do, and this isn't really good. There's also a lack of scalability, not too much analytics available for vector data. This is why you kind of need a purpose-built vector database, and a little bit of why Milvus got to set ourselves apart here a little bit. Milvus is designed to be a cloud native from the start. It's fully separates its storage and compute, meaning that it uses worker nodes that are stateless for all the operations that occur. So you can scale out each part of your cluster. Let's say you're indexing a lot, you can scale out your indexing nodes. If you're inserting a lot, scale out your data nodes. And if you're searching a lot, you can scale out your query nodes. And if you're not doing any of those, you can scale them down. In addition to this, we support a bunch of different indexes and GPU acceleration, recently thanks to NVIDIA's help in our project. And with our vector database, we've also open sourced our search library, which I think is pretty important. And speaking of search library, quickly going to go over sort of what's going on internally in these vector databases, how these searches are performed. I'm going to go over 3 of the main libraries, which are Annoy, Face, and HNSW. Annoy is a tree-based algorithm. It works by pretty much splitting all your data with hyperplanes repeatedly to make a tree, and then creating a forest of those trees. So when you search for a vector, you kind of go down, okay, is this vector closer to this side or the other side? And you continuously go down until you find your top K results at the bottom. And then you reduce across all your trees to make sure you're hitting everything. This is a pretty fun one. And this one was developed by Spotify at a hackathon, which is pretty cool. I think it was in a few days, one of the Spotify engineers made this algorithm. It was one of the earlier ones in this sphere. The next one is an inverted file index, or IDF. A very popular library for this is Face from Facebook. And this is pretty much just a general clustering algorithm. It's k-means clustering, where you split up your data into multiple clusters. And when you're performing a search, you just compare across clusters to find your closest centroid, and you grab the data from there, your top however many you're looking for. And this image kind of represents what those clusters look like in a 2D space. It's called a Voronoi diagram. Pretty cool to look at, and you can kind of generate this across your data as well. And with IVF comes the ability to quantize. Most of the other indexing algorithms allow quantization, which is sort of compressing your data in order to create smaller and faster indexes. And then lastly, which I think is pretty much used by all of the vector databases, or probably like 95% of the vector databases, is HNSW. It's probably the fastest and the easiest one to use. It's based on a skip list and a navigable small world graph kind of combined together. That's where you get the HNSW name. And this is just a multi-layer graph where layers at the top are very sparsely connected. So you can kind of make big jumps. And then as you go down, every time you jump, you go down a layer to a more connected graph. So you're kind of starting really wide, making big jumps if you're looking for a similar vector. And then as you go down, you narrow down to a certain space and you end up finding your closest matches. This was just a pretty quick outline of all of the indexing algorithms and sort of what's going on inside. There's a lot more details online. I think it's a really interesting subject, so you should check it out. Not really too applicable to computer vision, but it's always useful to know. So now I'll start going over kind of the main and first vision use case that vector databases were used for. And this is computer vision, reverse image search, sorry. How does it work? There usually comes in the form of 3 steps, with the 3 main steps being segmentation, embedding, and search. Segmentation isn't always needed. Segmentation is mainly used when you want to kind of narrow down what you're looking for within an image. If you don't care about that, you can skip this step and immediately embed your image. Embedding is converting those segments or your entire image itself into this vector that's easily comparable. And searching is just taking a search image, embedding it as well, and then taking the vector that you're searching for and searching it across all your stored vectors. This pipeline is sort of used in most vector database applications. It's the same similar embed than search pipeline. So I want to start off by going a little bit into what segmentation is, when to use it, when not to use it, and what kind of types there are. So in the first case we have here is no segmentation. So let's say we're doing a clothing search or a fashion search. If you have no segmentation, you have a lot of noise in your image. So in this case, if you take a general model and you try to embed your image, the model might be catching on more to the car, the tire, the pavement, the background, and not the actual clothing itself. So if you're going for a specific domain, let's say like a small subset of your image, no segmentation isn't going to be too great. In another case, let's say you're going for a scenic view. Let's say you have two pictures of mountains, or you have a picture of a mountain and a database of mountains. There's not too much data that you want to extract from this image because you're going to be using all of it. You're going to be using the surroundings, you're going to be using the background, you're going to be using the weather, and you're going to be using all those details to find the most similar image. So there, you don't want to segment anything out. But in this case, you do. So once you decide on segmenting, there's two different ways of going about this. There's generic segmentation, and there's also domain-specific segmentation. Generic segmentation is a pretty recent one. I think one of the main models that was lately was released was the SAM model from Facebook, which is the segment anything model. And this model allows you to pretty much segment anything in the photo. So every object is going to be segmented out. This is pretty good because you don't have to actually train up your segmentation model, but it's also pretty bad because it will extract everything. So you kind of end up in a similar situation to not using segmentation at all. You're just pulling out every single detail, so pretty much you have a bunch of noise. But this still allows you to go in and search those specific items in the photo. So in this case, in the generic items photo, you still have a pair of pants that will most likely match closest to if someone's searching for a pair of pants. Yes, there's a lot of extra data that you're going to be wasting compute on to search over, but it's still a better result than just doing the entire image itself. Lastly, there is domain-specific segmentation. And here you are segmenting based on exactly what you want. So you train up a model that extracts the key details from the image that you are searching for. This route is usually the best because it saves a lot of compute, and it also saves, it also gives you the best results because you're pulling out the key detail that you want. The only issue is here that not everyone can train a custom model. It takes clean data, it takes a lot of data, and you need to mess around with it a bunch. It's not really a kind of plug and chug solution. So this is kind of what the choices you have are in segmentation. Each one has its pros and cons. You kind of have to decide where you want to go with that. The next step is generating the actual embeddings. And for this step, how embeddings work is you pretty much take an embedding model. And in the case of computer vision, you take an image. It's usually a CNN model, and you cut off the final layer to get the latent space sort of in the model. And you take that as an embedding. You flatten it out, and that's your embedding. The same problems as segmentation sort of occur here in terms of generic versus domain specific. If you take a generic model and you segment a pair of pants, that model might not know. It might be too generalized of a model to know, okay, I'm looking at pants. And then when I say like these, like what I'm guessing a model's seeing, the model's a black box, you don't know anything what's going on. But let's say if you have two pairs of black pants, the model might see, oh, it's just a black blob. And they'll match it, but it'll also match a pair of black shoes and a pair of black pants. If you have a more domain-specific model where most of the model has been trained for embedding articles of clothing, it will most likely know to pull out the finer details from the image that you're looking at. So as a result, you're probably going to get much better embeddings. This, again, is a trade-off. Not everyone can train their own models. I believe training models for embedding are a bit simpler than training models for segmentation. So it's not as hard of a problem because a lot of the cases are just train a classification model and then kind of generalize it to embedding generation. But it's another problem that as a kind of a computer vision engineer, you have to decide which route you want to go down. And the final step is just the search that goes on in the vector database. This step is data agnostic. The vector database doesn't really care where your data is coming from. It doesn't care if it's looking at embedding of a dog or a shoe. It just knows one thing, and that's how to find the nearest matches of the vector, the actual mathematical matches. And with vector databases and the actual search, there is this trade-off similar to the CAP theorem in distributed systems, which is performance versus recall versus price. You can only pick two. You can have a fast and accurate index and a fast and accurate search, but most likely you're going to be paying for a lot of memory and CPU usage. In the same way, you can have a high recall and price, but you can still make it slow, but no one really chooses that one. But in general, you can only choose two, and you're going to either want to go for price versus recall. It's pretty much about how much do you care about how accurate your results are versus how much you're spending on your memory? When it comes to the indexes itself, there's also the switch of choosing which different distance metrics you want to use. I listed 3 of them here. IP and cosine are pretty similar on normalized data, but in general, what you're looking at is do you care more about the direction of the vector, or do you care more about the distance between the vectors? In a lot of use cases, I believe text is one of the main ones. You're not really caring too much about the distance. You're caring more that they're in the same direction so that the word sort of has the same meaning. And yeah, that's kind of the options that you have in the search step of things. And this is sort of what the pipeline looks overall. So the transform into vector step, just imagine segmentation and embedding right there. So you first transform your vectors, you store them, you transform your data into vectors, store them in the vector database. And then when a query comes in, whatever type it is, you use the same model, the same pipeline to generate the embeddings. And instead of storing them in the vector database, you search against the vector database. And yeah, that's again in computer vision, in text search, in video search, audio search, pretty much any pipeline. And then just to kind of like give more ideas of where this is going on, I would say pre-LLMs, before this whole kind of wave of GPT and all that, e-commerce was our most popular use case with Milvus, and it was mostly in terms of product search. It started first as text search, so getting word embeddings for a search and then searching it against the description, the word embed or the embedding of the description of the item. But then as people started to move to this, they thought, why not move to images as well? A lot of users may want to search by, oh, I have a photo of this chair. I want to find a similar chair. And that's where that started. So then slowly e-commerce platforms started adding the ability to search for items based on images. And this was pretty cool. And then once Clip came out, so Clip is a model, I don't remember who released the model, but it allows for text to image and image to image search. And this pretty much fused both pipelines together into one. So you can search by image or by text. I would say this is one of the most popular kind of models used in the e-commerce sphere and in the e-commerce sphere when you're dealing with vector databases. And then another popular use case found predominantly in law and finance is kind of patent search and copyright search. And this can happen in the form of text or image search. So a big one is logos. We had a big user who was using a vector database and their pipeline for images to search for kind of copyrighted logos. If someone was copying another logo, if the logo was found in an image. And this kind of speeds up things because it's not a manual person looking over and seeing if a logo popped up somewhere. Let's say you're in a lawsuit and there's a bunch of discovery that you have to search through. You apply this and you can find out much quicker if there are any correlations going on in your data. The last one, but a cool one, is autonomous driving. Not too many users of this, but there were kind of some POCs and some cool uses of using vector databases to go over kind of your driving data. So let's say your car is driving, it has a classification model to know, okay, am I seeing a car? Am I seeing a dog? Am I seeing whatever? But sometimes the classification model doesn't generalize to everything too well. If you train it with too much data, it begins to kind of lose some of its details. And this is where sometimes it might see something with low confidence. So in this case, if you have all of what you've seen before stored in a vector database and your actions associated with what you've seen before, you can search for a new, let's say you see a new object, you don't know what it is, and you don't know how to decide what to do. If you search it against your database, you can see, okay, what's the closest object, or what are the top 5 closest objects? What did I do there? And you can kind of re-rank your choice from there. Again, similar pipelines throughout all these things, but pretty cool use cases. The next use case, or I guess a use pipeline, is reverse video search. And this one I would say is kind of more state of the art at the moment. More work is popping out every day for this. And the reason is because computer vision in terms of like image problems are sort of solved. We've gotten to the point where we know how to do most things, and it's not as big of a problem anymore. There are models for all these segmentations for embedding generation. There's good generalized models. And the problem's sort of been solved. Sure, we can maybe increase the throughput of a new model that has a similar score, but the throughputs of a lot of these models have been pretty high lately. So the next step is video. And video is pretty hard because you have an extra dimension of time. And processing this is very, very hard because in most cases with these models, instead of processing one image, you're processing a matrix of, let's say, 30 images or 200 images based on whatever time period you selected. And this gets very expensive in terms of compute, so you need more efficient models to do these embedding generation. Another thing is that with video in the time dimension, you have the problem of needing to remember. So there's long-term dependencies across your video that the model needs to take advantage of. And this is a hard one to kind of get over with embeddings, because with embeddings, you're normally breaking up your video into chunks. And once you do chunks, you lose kind of previous information. And the biggest one out of all of these, I think, is the lack of meaningful data. Not too much work has been done in labeling video data. So if you want to start making these models, you might have to build up your own data source. And that's always really painful, especially with videos. And this is sort of where large language models have their strength, because they can do all this because they act on unlabeled data. Unfortunately, for now, I don't think there's been any unsupervised learning for video models. And then what the pipeline looks like, it's all pretty similar. Instead of just searching for an image, you're breaking down a video into multiple frames, combining the frames together, and then generating the embedding across that chunk of frames. There are a few popular models. Clip for clip is a big one. It pretty much takes clips, so the reverse image search and text search kind of multimodal model, and allows you to do it on video. I have a demo of this one that I'll present, I think, after this slide, but that's probably the coolest one right now. And it also allows for video to video search. There's X3D, which is sort of a expanding 2D model. I believe it's one of the first video classification models, but it pretty much works like a 2D model, but it slowly expands over your data. So it starts with like a small, maybe one frame in one part of a frame, and slowly expands through all the dimensions. So expands through the size of the frame and also the time in the frame. And there's video MAE, which is an autoencoder for videos. And all of these can be used to generate embeddings by taking the latent space. In production, we haven't seen too much of this. People have been coming and asking about it and seeing if they can do it. So we've kind of built up some pipelines with our TOEI project, which is that ETL pipelining software. We built up projects to kind of test these models and test the feasibility of running these pipelines. And the big ones that we see are for large scale video search. So companies hoarding a bunch of video data. How can we search through it? Maybe it's video cameras, maybe it's security systems. Video recommendation. This can be like in all the kind of providers of content. You can see what someone's looking at, and you can do a reverse video search and see similar videos and recommend those. Scene deduplication. So if you're getting a lot of duplication in your videos or a lot of duplicated frames, so let's say you're compressing video, you can kind of dedupe it, which is pretty useful. And then targeted advertising, which is similar to video recommendation. And now I'll quickly go over a few demos. I pre-computed the demos. I'm currently on my laptop, so I won't actually show the computation scene. First, I'll show the actual demo and then kind of go into the code. We can sort of begin with the reverse image search, and I did this one in Voxel, just for an easy way to display it. Hopefully my computer loads it up. So this pipeline was a segmentation combined with clip. And what this means is I can segment out the images, as you can see, and pull out all the key details. And this was segmented using a fashion model. I'll show the code right after. And what it allows you to do is take a look at all your data in terms of items. And let's say if I want to look for similar shoes, I can go do a similarity search with Voxel, and it will show all the shoes. And then let's say in this image, I want to see the full image. You can see where it came from. So I think that's Kanye. But this is probably the biggest use case of reverse image search in terms of kind of e-commerce, finding clothing, finding products. It will also let you search with text, since it's a clip model, for images of shoes, and it will find the shoes for you, which is pretty cool. And I can quickly go over the code and what's going on here. It's a pretty simple script. So sorry, I know always going line by line through code instead of slides is a lot harder to view, but I wasn't sure if I'd have time in the slides to show it off. So pretty much what it comes down to is you have a segmentation model, and you take the segmentation model. So in this case, we have these three functions: get segmentation, get mask, and get bounding boxes. So the segmentation model finds the segmentation, the masking model pulls out the segmentation. So kind of when you highlight the data, the masking model actually takes out the highlight, and then you just turn that into bounding boxes. And with the bounding boxes, what you can do is you can put them into the voxel data set and label them as detections. And that's how you kind of get your patches in voxel. And you can do the, so in my case, I did the clip model, which allows searching for the patches using either text or image. And that's how you get the multimodal search. The next kind of demo I'll kind of display here is a demo of the reverse video search. So this is the clip for clip video pipeline. So in this case, I think it's 1,000 video snippets. I forgot the dataset name, but I can search for, let's say, a happy cat. And it will find, I'm not sure. So the closest result is one with a cat in it. Doesn't look too happy, but I think that's one of the few actual cat data points in the dataset. So if you want to find a happy dog, it can go and find some videos of dogs. And I'm assuming here the dog is happy because the lady is happy. But yeah, those are kind of the pipelines. And for this, I can quickly go over the code. This one's more advanced. This one's using the Tohi project that I talked about. What we're pretty much doing is all your data comes in the form of a video and a sentence describing the video. So pretty much if you take a look here, this is what our data looks like. It's compressed into a GIF, but it's a video. And then in this case, a girl wearing red top and black trousers putting a sweater on a dog. And then here is creating our vector database. Not too important. And this is our pipeline. And in our pipeline for storage, we are taking the videos, extracting the frames, putting that extracted frame through the clip model, and inserting the vector into Milvus. And then for the search, we're doing the same thing, but instead of searching, instead of inputting it into the database, we are searching against the database. And yeah, I think I have a few slides to finish off. I might have closed them. I closed my slides, but yeah, it's just a few links to our project. Let me see if I can actually open them up real quick. Sorry about that. Profile right there. There we go. I'll just keep it in slide format. So if you want to get started, here are some links to our project. And yeah, so the vector database benchmark, kind of compare all these vector databases. All our open source projects can be found in the third link. Our integration, which was recently released with Voxel, is available as well. And yeah, the first link is to kind of learn more about Milvus. And here is a quick QR code. And finally, thanks for watching. And I see a question in Zoom. So the question is, in the example where you search to find similar shoes, in this case, do you have embeddings generated for the individual objects? I think patches and voxels too, or just image-wide embeddings? In this case, what I'm doing is just the patches. I don't do image-wide embeddings because in this case, I've determined the image-wide embeddings aren't too useful. Because in this model, I'm also using clip, which isn't fine-tuned for fashion data. So I don't really want to use it to kind of create an embedding of everything because it's a little bit too generic. So yeah, only on the patches in Voxel. And yeah, I think that's right on time, 30-minute mark.
Yeah, well done. So it looks like that's all the questions queued out or in the queue. No, it looks like there's one more burning.
Oh, I may have accidentally closed it. Oh. Does Voxel similarity checker work On Milvus. Yeah, so Milvus has an integration that was recently released. I believe there was also a kind of guide on Voxel's site, but also released this files that I showed. So you can kind of check it out for yourself as well.